Hi everyone, this is our fourth lesson on limits, and today we're going to talk basically about algebra. We're going to talk about how to do limits without a graph, without a table, just with an equation using algebra. So the first strategy always when you're trying to find a limit is to plug the arrow number in to the equation and see if you can get an answer. That's what we mean by direct substitution. It simply means plug the arrow number in. The arrow number is the number next to the arrow, right? So this is my way of calling this number right here. In this problem, 3 is going to be your arrow number, right? So for this equation right here, I could just simply plug in 3 and see if I get an answer. So if I plug in 3, I get 3 squared minus 7 times 3 plus 4. Remember, PEMDAS is important. So this is 9 minus 21 plus 4. You're going to do this left to right. This is not 9 minus 25. This is 9 minus 21, which is negative 12, plus 4, which is negative 8. And we get a meaningful answer, and so that's it. We're done. That's the limit of that polynomial, that quadratic, this quadratic equation. As x goes to 3, the y value will go to negative 8. And that makes perfect sense because this polynomial is a quadratic equation. It's continuous everywhere, right? So the limit value at any particular arrow number is going to be equal to the function value at that arrow number, right? So I'll come back to this in a minute. Let's work a couple more examples. First, let me do this one right here. So here we have actually, let's go down. No, let's do this one. Here we have a rational function, right? So always look at the function and use your pre-calc and algebra skills to kind of know something about the function before you start plugging things in blindly. So you can immediately see that this is a rational function. That means it's got a top and a bottom and it looks like a fraction, okay? So a rational function is going to have some discontinuities, right? We know that rational functions can have wholes, rational functions can have vertical asymptotes. In this particular case, nothing cancels as a factor on top and bottom. And so what we have here is we have a rational function with two vertical asymptotes, one at x is equal to 1 and one at x is equal to negative 1. Now, if those were arrow numbers, then we would potentially, we wouldn't be able to just use direct substitution. We couldn't just plug the arrow number in. However, those are not the arrow numbers. The arrow number is 5. This function is going to be continuous at x is equal to 5. There's no whole, no vertical asymptote. So you're going to be able to just do this. 3 times 5 plus 1 over 5 minus 1 times 5 plus 1. This is going to be 16 divided by 4 times 6. You can cancel and get 2/3 as your answer. And yeah, that's another example of direct substitution. Let's move on to some other functions. I've chosen all these different functions to kind of jog your memory about the various types of functions that you know how to handle from pre-calc, right? Okay, let's take a look at this one. This is a trig function, and let me see if I can do direct substitution. That would be doing tan 0 plus secant 0. Tangent of 0 is 0. Secant of 0, secant means 1 divided by cosine. So I really am trying to do 1 over cosine of 0. Cosine of 0 is 1. And so this is 0 plus 1 or 1. So yes, I got a meaningful answer. I'm done. That's the answer to that limit problem. Okay, let's move on to this. We've got a square root function. It's actually a square root function. That's this guy, right, rad x, and we're shifted right by 2. So this function really looks like that. It's good to kind of think about that. You don't need it, though, to do the problem. The problem is simply done by taking 11, putting it in there. So we get square root of 11 minus 2, which is square root of 9, which is 3. Remember that the square root just means the positive square root. It's not plus or minus 3, it's just plus 3. Okay, let's do another one. Exponential. Let's see if we can do direct substitution. E to the 1, arrow number is 1, so I'm plugging in 1 plus e to the negative 1. E to the 1 is e. E to the negative 1 is written as 1 over e, right? And this, you're going to leave this answer just like this, right? We know that this is roughly 2.7 plus 1 divided by 2.7. So if we need a number, we can get it. But in an algebra problem, you're allowed to leave e's and pi's in your answer. So we're done with that. That worked out fine. Arctan. Okay, so let's see. Do we know, can we do arctangent of 1? I always say about arctan, if there's one thing that you want to remember, it is that the arctangent of 1 is equal to pi over 4. If there's one thing about the arctan function that you want to remember, right? So let me quickly remind you what this even means. You have your unit circle. You're at this place right here where the sine and the cosine are both rad 2 over 2. Therefore, the tangent is equal to 1, right? So we're at that particular angle where tangent is equal to 1. And when we say arctan, arc or tangent inverse is reading this unit circle backwards. So I'm giving you this number. I'm saying the tangent is equal to 1 somewhere on the unit circle. What is the angle, right? So you know that this angle is going to be pi over 4. So that's how arctan or tangent inverse works. These are all pre-calc skills, and technically I shouldn't have to even explain these, but I try to use some of these problems as an opportunity to review your pre-calc skills. Okay, so this is equal to pi over 4. And remember, you can leave pi in your answer. And so that's our final answer there. So in all of these problems, we were able to put in the number and get out an answer, right? So this will happen whenever f of x, the function, is continuous at the arrow number, right? So that's going to happen for polynomials everywhere. Polynomials are continuous everywhere. Rational functions are continuous when the arrow number is in the domain of the function, which means that we're not at an excluded value. We're not at a whole, and we're not at a vertical asymptote. So this will work. Rational functions are continuous everywhere in their domain. Square root functions are continuous everywhere in their domain, right? So what do we mean by that? We mean, well, if you've got the square root function like this is just rad x. This is continuous. There's no breaks or holes or asymptotes in the domain. This side, x is less than 0, is not in the domain. So obviously, we cannot make the statement that we're continuous there, but we are continuous in the domain, which is x is greater than 0 for the square root function. Okay, greater than or equal. Then trig functions, again, when the arrow number is in the domain. That tangent function that we did here, right? If you had tried to do the limit of the function as x is approaching one of the asymptotes. Remember the tangent function and the secant function, they have asymptotes, right? So the function is not going to be continuous when you are at an asymptote. But if you're in the domain, right, which is the part which is between the asymptotes, you're going to get away by just putting in the arrow number and getting out an answer. Inverse trig functions, exponential functions, log functions, all these functions, basically everything down here is continuous in the domain, right? Polynomials are continuous everywhere. So for all these functions, you are able to just plug in the arrow number, get out an answer. We're going to talk about this more, this little equation here later. But what you're doing is just evaluating the function at the arrow number, getting out an answer. Okay, what happens when that doesn't work? Well, when that doesn't work, you're usually going to get something like 0 divided by 0 when you put the arrow number in. So when you get a 0 over 0, please remember that that does not mean that the answer is a DNE. It also does not mean that the answer is 0. It does not mean that the answer is infinity. It means that you need to find the limit through algebra. You need to try to do factoring or rationalizing, simplifying something to try to find the limit. Okay, so let's begin with a couple of factoring problems. You practiced this on your summer packet and you've done this in pre-calc, but let's review here for this first example. In the box, you have all our factoring formulas that you might need to use. You need to be comfortable with those. And here in example A here, let's try to see what happens when we put the arrow number in, right? So always try to put the arrow number in, but in this case, when you do that, you get 4 minus 4 over 2 minus 2, or 0 over 0, which means we have to do something, do some algebra. This problem is just crying out to be factored, so you can factor the top with a difference of 2 squares, and the bottom stays how it is. But now, once you factor the top, you can cancel this factor, x minus 2. And now you're able to put the 2 arrow number in to what is left, right? And get a meaningful answer out. The answer is 4. And that's the answer to the limit problem. Notice that in terms of notation, we're writing this limit notation until the step where you can put the arrow number in. And then you stop writing limit and you write the answer. Okay, let's do this one right here. So this one, you can do like this. We can say this is the limit as x goes to 1. And on top, you might not notice it at first, but you can realize that this actually can be factored if we think about it as rad x, the quantity squared, minus 1 squared. So it is really an a squared minus b squared, which can be factored into a minus b times a plus b. So this is the kind of sort of tricky or more advanced algebra that you need to start looking for and mastering in calculus. And when you do that, you're going to be able to cancel the factor on top and bottom. And now you can put the 1 in and get square root of 1 plus 1, which is 2. I skipped the actually direct substitution checking, but if you just put this 1 in, you can see you get 1 minus 1 over 1 minus 1, or 0 over 0. So I may not always say that, but the implication is you're always trying the direct substitution. When it doesn't work, you're then moving on to algebra. Here, this is going to be, again, put the direct substitution, get 3 minus 3 over 27 minus 27, 0 over 0, right? So we've got to do some factoring. This is going to be a difference of cubes, which I can see right here, because this is theta cubed minus 3 cubed, right? So I use the difference of cubes formula, and that is going to be, the way I do that is I always do, I do two factors, a linear factor and a quadratic factor. The linear factor has the same sign. The quadratic factor has first the same as this right here, opposite sign and always positive. And then in here goes a. The a here is theta and the b is 3, right? So theta minus 3. And then here you get a squared and b squared on the two ends and ab in the middle, right? So that's that. This now cancels. When you cancel, remember that you're left with a 1. And so now I try to put the arrow number in, and I get 1 divided by 9 plus 9 plus 9, or 1 over 27. Okay. Let's take a look at this guy. Some of these I'll just give you the strategy. I won't work it all the way to the end. Direct substitution again, you get 1 minus 1 over 1 minus 1, so 0 over 0, so we got a factor. Here the strategy will be to do this. You'll go s to the fourth minus 1. You first think of that as s squared squared minus 1 squared, right? So this is a minus b times a plus b. That's going to be your first factoring. And then you're going to do this guy again as a difference of 2 squares, right? S minus 1, s plus 1, and then s squared plus 1. And then on the bottom, s minus 1. These are going to cancel. You can put the 1 in, and you get 2 times 2, or 4, as your answer. This guy right here, you're going to do quadratic factoring on the bottom. I'm going to go through this just so that you understand. Again, a very important thing, which is to know how to factor a quadratic which has a number other than 1 out here in the leading coefficient. Okay, so on the top here, that's a difference of 2 squares, so that's pretty straightforward, right? On the bottom, I want to remind you, how do we factor this? Let's just make sure. Yeah, so this is what we're factoring. So remember, we are trying to find two numbers that multiply to 2 times 3, or 6, and they add to 7. So the two numbers are going to be 6 and 1, because 6 times 1 gives me 6, and 6 plus 1 gives me 7, right? So then I take the middle term here and I break it up into 6t plus 1t. So 6t plus 1t plus 3. And then I'm now going to factor by grouping these terms and these terms. So I get 2t times t plus 3, and here I pull out just a 1 times t plus 3. Always remember to pull out a plus or a minus there, so that now this and this get put together as the first factor, 2t plus 1, and this one, which will be the same, goes as your second factor, just one time, t plus 3. And guys, remember, the goal is that if you were to FOIL this thing out, you should get back this that we started with, right? So please always check and understand what you're doing. Okay, so 2t plus 1 and then t plus 3. The t plus 3 is going to cancel, and you can now put in negative 3, and you get negative 3 minus 3 on top, and 2 times negative 3 plus 1 on the bottom, negative 6 over negative 5, or 6/5 is our answer. This last one I have in here just to remind you to be careful with your signs. The top is 5 minus t times 5 minus t, and you got t minus 5 on the bottom. When you have 5 minus t and t minus 5, those can cancel to give a negative 1, right? And so final answer here, well, let me just rewrite it like this. I'll distribute that negative 1 now into this factor and get negative 5 plus t. And now when I put the arrow number in, I get 0. So a lot of algebra, and you've got to know how to factor efficiently. You've got to know how to remember all those factoring formulas and use them properly. Okay, expanding. Sometimes, actually, quite importantly in calculus, we're going to run into situations like this where you have, again, an equation. Remember that here it says h, but this is the same as if I were to write the same problem with x. It means exactly the same thing. We're going to be using different letters in there. Don't be confused by that. Okay, so I try to put in 0. I try to put in my arrow number. I'll get 3 plus 0 squared minus 9 over 0. This is 9. 3 squared minus 9 is 0. This part is 9, I'm sorry. 9 minus 9 is 0. 0 over 0 is basically an indeterminate form. I forgot to say that earlier, but we call 0 over 0 an indeterminate form. Again, it does not mean a D&E. It means we have to do algebra. So I'm going to expand 3 plus h, the quantity squared, right? You can do 3 plus h times 3 plus h, which is 9 plus 3h plus another 3h plus h squared, and then combine the central terms here to get 9 plus 6h plus h squared. But I highly recommend that now that you're calculus students, you start to recognize patterns like that so that you can go quickly from 3 plus h, the quantity squared, to 9 plus 6h plus h squared, right? As simple as that. You think of the 3 as the a and the h as the b in this formula. Okay, and so now we've got this. Cancel the 9's because 9 minus 9 is 0. And now you can factor out an h, and then you have 6 plus h on top, h on the bottom. And now notice I'm at a place where if I put in, after I cancel these h's, I can put in a 0 here and get out an answer of 6. Okay. Okay, this problem here is interesting for two reasons. The first reason is that it makes us review the expansion of a cubic binomial, right? With Pascal's expansion. Those of you who had me in algebra, you remember us doing this. The other reason this problem is interesting is that our answer here is going to come out not to be a number, like we've seen all these limits that came out to be numbers, or most of our limits at this stage in the course are coming out to be numbers. The answer here is going to be a function, and the function variable is this, theta, right? Because you can see this guy is your arrow number variable, right? But you have this other variable in the problem. If you compare it to the problem we did here, here you have the arrow number variable and the rest of the problem is numbers, right? So the answer here will be a number. When you have a problem like this, the limit answer is going to be actually a function. And we're going to talk for the rest of the course, honestly, about what that really means. It's going to be the derivative. But let me just show you how to do this limit problem. So if you try to put the arrow number in, that's our first strategy always. You get theta cubed minus theta cubed because the arrow number is 0 over 0, right? Which is 0 over 0. So we need to do algebra. Theta plus h, the quantity cubed, I've given you Pascal's expansion here. It's like theta plus h, the quantity cubed, and I'm going to use this formula to expand it. So we're going to get, this is going to be theta cubed. Oh, not h goes to theta, h goes to 0. Remember, write the notation properly. We have to keep the limit going until the very end. Expand the binomial, theta cubed plus 3 theta squared h plus 3h squared theta plus h cubed minus theta cubed all over h. These two theta cubes on the end cancel. And similar to the last problem, we're not done yet because at this stage, if you try to put in h equals 0, you're still going to get 0 on top and 0 on the bottom, right? So you're going to have to factor now. You're noticing there's an h here and an h here and an h here, so you can pull out an h. And when you do that, that h is going to cancel with the h in the denominator. And that's how we're going to get rid of our 0 over 0 problem. And now you can put the h equals 0 in, right? This term will become 0. When you put 0 in, this term will become 0, and you'll be left with 3 theta squared, right? So we took a function, theta cubed, really at the beginning, and we found that the limit as h goes to 0 comes out to be another function, 3 theta squared. Make this lesson too long. Oh, it was a number. Okay. Let's go now to a couple of conjugate examples. I'll just do 2 here. Conjugate means rad A plus B. The conjugate is rad A minus B. Conjugate of rad A plus rad B is rad A minus rad B, right? So what is changing is the sign that's connecting the two terms. So when you see a problem that has square roots, and notice, again, I put in the direct substitution. Always my first strategy is that, right? So direct substitution, let's see what happens. Well, I get a 0 on the bottom. On the top, 16 plus 9 under the square root, that's 5 minus 5. Remember, this is just the positive square root. So I get 0 over 0, right? So that means I have to do something. The thing you'll be doing when you have radicals like this, right? You want to immediately think of multiplying by the conjugate of the term that has the radical. This is the term that has the radical, right? So its conjugate is going to be just change the sign of what holds that binomial together, right? So that's the conjugate. Don't forget to do the exact same thing on the bottom, because the strategy here is we are just rewriting this function. We're not changing it. We're not allowed to change it because we need to find the limit of this function, right? But notice that if you do this here, all you've done is multiply by 1. That's all we've done. We've not changed the function. So you do that, and then when you multiply by the conjugate, what happens is that you're running the difference of two squares backwards, right? So it's, let's see if I can highlight these. It's a minus b times a plus b, right? So you get a squared minus b squared on top. So a squared, when you have the square root of x squared plus 9, and that's this right here is your a. So a squared just takes away the square root, and that's the beauty of multiplying by the conjugate. So we get x squared plus 9 minus, be careful, b is 5, so minus 25 over x plus 4. Limit as x goes to negative 4. Notice my notation, guys. I haven't said that yet in this video, but it's very important that you don't just drop the limit. You'd only drop that limit, these words here, when you get to the end. And by the end, I mean when you can successfully put the arrow number in and not get 0 over 0. Okay. So let's see, now I'm still simplifying. I'm not at the end. So I get x squared minus 16 over x plus 4. At this point, if you try to put the negative 4 in, you're still getting 0 over 0. So now you're going to factor, right? So this is an example where you had to kind of do more than one thing here. You had to first multiply by the conjugate, then you had to factor, and now finally you can put that arrow number in. Now is where you stop writing limit and you just write an answer. Negative 4 minus 4 is negative 8. And that's our answer. Okay, let's see. These are pretty much the same, B and D. Let's talk a little bit about C. C, you're seeing your square roots up here, right? So the conjugate of the thing on the top will be, notice this is like, you know, a minus b, right? So the conjugate is going to be a plus b. So it's going to be rad 1 plus t plus rad 1 minus t. And on the bottom, you have to do the same thing. Okay, now we are looking at this as a minus b and this as a plus b. So when you multiply them, you get a squared minus b squared. And so I get a squared, which is 1 plus t, minus, be careful with the minus sign, it has to distribute to that 1 minus t. And on the bottom, you have all of this stuff. Don't forget that. Okay. So on the top, now you have, notice my notation again, I'm not dropping the limit notation until the end, 1 plus t minus 1 plus t over, on the bottom, t times rad 1 plus t plus rad 1 minus t. These ones go away, and I have now 2t on the top and t on the bottom. And I can cancel these t's, and that's fantastic because now I can put the t equals 0. If I didn't cancel the t's, I'm again getting 0 over 0, right? So the point of all the algebra is to get to a place where you can put the arrow number in, and I'm finally at that place. I can stop writing the limit, and I go 2 over square root of 1 plus 0, which is just 1, and square root of 1 minus 0, which is just 1. So it becomes 2 over 2, which is 1. Okay, last type of thing, last type of algebra that we're going to run into with 0 over 0 problems is simplifying fractions, right? So you might have fractions just like this, or you might have fractions like this, right? Which is a complex fraction. So let's do the first one. Here, notice, first of all, if you try to put t is equal to 0, you're getting things like 1 over 0 minus 1 over 0, right? This looks like, we don't even know. You cannot divide by 0, right? So sometimes you won't get 0 over 0. You're just getting a 0 in the denominator. But when you see that and you see that you can simplify the equation, let's try to see if that helps us to be able to put in the arrow number. So I'm going to combine these. I'm going to say the denominator is t times t squared plus t. And now I made a common denominator, right? So I have to multiply the left side by t squared plus t on the top and bottom, and the right side by t, right? So I'll end up with this. The t's will cancel, right? So now I have the limit as t goes to 0 of t squared over t times t squared plus t. Notice this is a little weird problem because I have to now pull out another t from here. I can cancel one t first and then pull out, or I can just pull out first and then cancel. So I'm going to pull a t out of here. This guy becomes t times t plus 1, right? And this t multiply to give me t squared. So I have something like this. These cancel, and I'm left with 1 divided by, now I can put the arrow number in, 1 divided by 1 is 1. Okay, I think this is going to be my last example right here. How do we do this? Well, here we have a complex fraction. That means a bunch of fraction stuff over a big bar and another either just one term or potentially fractions on the bottom as well. If you try to put in 0 over the arrow number, which is 0, you get 1 over 2 minus 1/2 over 0, right? So 0 over 0, not an answer, need to do algebra. Let's simplify the fraction on top. So on top, 1 over 2 plus x minus 1/2. Make a common denominator. The common denominator will be 2 plus x times 2. Left side needs to be multiplied by 2. Right side needs to be multiplied by 2 plus x. Be careful with the negative sign. And that's what we have. So now we have limit as x goes to 0. Distribute this thing properly. 2 minus 2 is 0. Negative x over 2 plus x times 2. That's on top. And x on the bottom. So remember from your Algebra 2 days that when you have here a fraction divided by another thing which doesn't look like a fraction, but I can think of it as a fraction, we're going to do keep, change, flip, or multiply by the reciprocal, whatever you think of that as. So the top stays the same and the bottom gets flipped, and I'm now doing a multiply. Now these x's cancel, which is what I'm hoping and waiting for, because once they cancel, I can put the arrow number in and I get negative 1 over 2 times 2 plus 0, which is 2, so negative 1/4. Okay, so those are all our different techniques to find the limit using algebra. The takeaways are that to find a limit with algebra, the first thing you try is direct substitution, which means plug that arrow number into the equation and see if you can get an answer. If you can get an answer, you're done. If you cannot get an answer, in other words, you get 0 over 0, this does not mean that the limit does not exist. This does not mean that the limit is D and E. It means you need to do some more work. You need to do some more algebra to find the limit. The algebra methods that you need to be comfortable with and master are factoring, rationalizing, expanding, right, and simplifying complex fractions. And I hope that you enjoyed that lesson, and I will see you / talk to you very soon. Have a fantastic day. This is a little addendum actually to this video, and this is about trig identities, because sometimes we're going to need to be using some trig identities to do a limit, and so I just wanted to give you a couple of examples of that. So you've got the trig identities in your notes, the ones that might come up, and we're talking, the mother of all trig identities, sine squared plus cosine squared x is equal to 1. You want to know that one. And then some of these are simply definitions, like tan x equals sine x over cosine x. So you have these different identities in your notes. One that you may or may not have seen before that's pretty useful is the double angle formulas. Cosine of 2x is equal to cosine squared x minus sine squared x. So here we have that double angle. And then using the Pythagorean, identity, we can rewrite this a couple ways, right? Because remember, this identity here can be written as sine squared x equals 1 minus cosine squared x, or cosine squared x is equal to 1 minus sine squared x. So if we use this identity now in here and substitute 1 minus cosine squared x for sine squared, we're going to end up with 2 cosine squared x minus 1. And then if you use instead now this identity here and substitute that in for cosine squared in the double angle formula, you would end up with 1 minus 2 sine squared x. Okay, so we can, sort of review these review these trig identities to be able to use them fluently, but they are going to come into play doing some limit problems. So let me do 3 examples. The first one is the limit of tan x over sine x as x goes to 0. So always remembering that your first method is put the arrow number in, direct substitute, and see what happens. You would get tan 0 over sine 0, which you should know from your unit circle without a calculator, 0 over 0. That didn't work, so off we go with algebra. And the algebra here is going to be to write tan as sine over cosine. The denominator is sine. This is starting to look like a complex fraction if I think of the denominator as sine x over 1. So then I can keep change flip. And I'm going to notice that the sine x is going to cancel out. And I'm going to be left with 1 over cosine x. And this is something that I can put the 0 in here, put the arrow number in. I can direct substitute, and I can get a number out because cosine of 0 is simply 1. So my final answer here is 1. Okay, so that's my first trig identity example. Let's do a couple more. B is going to be the limit as x goes to pi over 4 of, let's see, 2 cosine squared x minus 1 over cosine x minus sine x. Now, this is where that double angle formula that I showed you up there, back up there, I'll write it again. Cosine 2x equals 2 cosine squared x minus 1, but it was also equal to cosine squared x minus sine squared x, right? So all these three things mean the same. This is going to come in handy here because now I can say that 2 cosine squared x minus 1 is the same as cosine squared x minus sine squared x. And if you're thinking, how am I going to know to do that? Well, this is where the creativity comes in. You're looking for a way to be able to figure this limit out. So you're just thinking like, what can I do? And you're thinking, well, I could rewrite this way. And if I do that, then I can use a difference of two squares, right? Here we have two squares and a difference. So we can use our difference of two squares to write this as cosine x minus sine x times cosine x plus sine x, right, all over cosine x minus sine x. And now we have a common factor that we can cancel. And now if you try putting the arrow number in, which I'm about to do here, you're going to be able to get a number out. Cosine pi over 4 plus sine over pi over 4, rad 2 over 2 plus rad 2 over 2 is equal to 2 rad 2 over 2, or just rad 2. Actually, it's even better to just think of this as 1 over rad 2 plus 1 over rad 2 is equal to 2 over rad 2, which is rad 2. Okay, so whichever way you think about that works the same. And we have our answer. Now, the whole thing starts with thinking, put the arrow number in. If you put this arrow number in, you would get 2. Cosine of pi over 4 is 1 over rad 2. You square that. So you got a 0 on top. And then on the bottom also you have a 0, right? So I've kind of mentally done that, realized it's 0 over 0, and that's when I jump into the algebra. Last one is here. Let's see, I have the limit as x goes to pi over 4 of cosine x minus sine x over 1 minus 2 sine squared x. So now, if you're familiar with the double angle formulas, right, you're going to again notice, oh, there I have it again. I can replace this denominator now with cosine squared x minus sine squared x. And now we can do some canceling. Again, factor and then cancel. So cosine x minus sine x on the bottom, cosine x minus sine x times cosine x plus sine x, difference of two squares. This guy cancels, and I have 1 over cosine plus sine. So now put arrow number in, 1 over rad 2 plus 1 over rad 2 is equal to 1 over 2 over rad 2, right? Because 1 over rad 2 times 2, which is basically what that is 2 over rad 2, which simplifies to just rad 2. So this is just 1 over rad 2, okay? Or if you insist on rationalizing, it would be rad 2 over 2. Okay, so these are just a few examples, and I guess we can add back up here to my takeaways that in addition to all these algebra methods, trig identities is a good strategy in finding limits also. Hope that helped. See you.